Thanks for the intro. So I'll talk about MoCE, which is a mixture of context-aware experts framework for troubleshooting internet scale services. And this is joint work with folks at Conviva, CMU, and Georgia Tech. So we all use internet services on a daily basis. And these are your apps for e-commerce, video streaming, social media, and so on. And underneath, these services run on very large and complex infrastructure, which involves millions of diverse components. And these components interact with each other in complex ways. And whenever you have such complex infrastructure, you're going to have failures. And these failures are costly. So this is a survey that shows that the hourly cost of failures in the average enterprise is about $300,000. So naturally, there is a lot of interest in resolving these failures quickly. Okay, so what kind of failures might arise in internet scale services? And you can think of internet scale services as comprising of 4 different high-level parts. So there are these clients, there is the network, there is the app backend, and then there are the third-party services that the app interacts with. And each of these parts are complex in themselves and can have different kinds of failures. And to detect those failures, you would typically collect telemetry data from different vantage points across these 4 parts. Okay. So let's look at some example failures from real-world internet services. So the first failure is where an ISP was adding delay to the packets that were transiting that ISP, and as a result, a large fraction of the users were not able to access the app. So this was on the network layer. The second failure is where a sequence of errors on the client-side device was resulting in a payment failure. So this failure was on the client side. And the third one was a backend service that was periodically failing at night, possibly due to some erroneous VM migration issues. And as you can see, I mean, this is by no means an exhaustive list. There are many more different types of failures that you might want to detect. And as you can see, these failures have diverse root causes. And to diagnose each one of them, you need different kind of telemetry data. Okay? And this failure diagnosis is also known as root cause analysis, or RCA. And this RCA at its heart is an inference problem. You have some failure type that you want to detect, and there is some telemetry data, and you devise an inference scheme to detect that failure type using the data that you have. Okay? So let me give some examples. So this is a system called Minesweeper, which looks at client-side events to diagnose application errors on the client. Okay? Then there's a set of work that finds the backend component that might be causing high response times, and this uses backend traces as the telemetry data. Then you have some systems that look at client-side metrics, and they diagnose anomalous performance metrics in the app. Okay? So and there are a few more of these schemes, and all of these are what I call as point solutions. They cater to one class of failures, and they have fixed telemetry data. Okay? But these point solutions are not enough, because they only capture one narrow failure class, whereas real systems have many diverse failure types. So this is not a comprehensive solution. And it's not only that, as your system evolves, you might introduce a new failure type or new telemetry data, and point solutions cannot adapt to either of those changes. Okay? So this has led to an impasse where we want to achieve a comprehensive RCA solution, but at this point, simply enhancing these point solutions will not get us there. And I claim that we need to look at this problem from a systems point of view rather than an algorithm development point of view. So we want to develop a framework that will enable the human analyst to express different kinds of RCA logic easily. And we want this framework to be expressive so that we can capture different types of failures and different types of telemetry. We want it to be extensible so that if there's a new failure type or new telemetry data, we can sort of extend the framework easily. And we want it to be scalable, because we are dealing with vast amounts of telemetry data here. Okay? So those are the 3 requirements for RCA. And to meet those requirements, we built this system called MoCE, which is based on 3 high-level ideas. And the first idea is what we call as mixture of context-aware experts. So a simple observation is that one algorithm isn't going to be sufficient to catch all failure types. So the more pragmatic approach is to use an ensemble or a mixture of experts approach, where you move away from point solutions and you move to a mixture of expert solution, and each expert caters to a subset of the failures. Okay. But if we naively do this, that doesn't quite solve the problem. So earlier, let's say you had one point solution, and now let's say you adopt a mixture with 10 experts, but that would require 10 times the computational cost, because you're running each expert, you're running 10 experts. And that would also require 10 times the human effort, because you need to develop each expert from scratch. So really, the systems, so that's not really a scalable solution. So really, the systems challenge here is how can we enable the mixture of experts solution in a scalable way. Okay? And that's where the second idea comes into picture. So we develop a framework which enables you to develop these experts easily. Okay? So we realize that for RCA, your experts need to be context aware, meaning you first need to narrow down the vast amount of telemetry data to the context of the incident. So for example, if your failure incident is high login duration for Android users, then you first want to narrow down the context to the set of events that happen during the login window in each session. Okay? And this is kind of a stateful operation, because you want to apply a filter based on what happened before. So naturally, it leads us to the question of what kind of data processing tools do you need to develop these kinds of experts. Okay? And I claim that any expert can be expressed as a DAG composed of 3 different types of operators. Okay? So either you have SQL operators or SQL-like operators to manipulate database tables, or you have stateful data processing steps which apply some stateful logic over sequences of events, or you have some statistical or algorithmic operations that apply some, let's say, machine learning logic or perform some data cleaning. Okay? And any expert, including those from previous works, you can think of them as a DAG composed of these 3 types of operations. Okay? And that gives us a way to think about the framework for the mixture of context-aware experts analysis. So essentially, the idea is we're going to have many experts, each of which look like a DAG. And we realized a lot of these operations are common or duplicated across experts. So we can merge the individual expert DAGs into sort of a large unified DAG. And that saves on duplicate computation. That also saves on duplicate development of these operators. Okay? And if you look at an individual expert, then each expert can be written very concisely in terms of its operators, if you have already defined those operators. So for example, in this slide, if you have already defined F1 to F6, then this expert can be very concisely written in terms of those operators. In fact, it is a very simple functional program in terms of those operators. Okay? And that allows us to design a framework that will enable rapid development of experts. So the idea is we'll have this library of operators, and you can compose them into new kinds of experts. And if you have an expressive library of operators, then you should be able to express diverse kinds of RCA logic using this. And this is a bit like Lego blocks. So your library of operators are like the Lego blocks, and you can compose them into new kinds of structures. Okay? So let me give some examples of these operators. So this is an algorithmic operator which takes as input a set of event sequences, and these sequences correspond to sessions. So each session is marked with a good outcome or a bad outcome. So a good outcome is, let's say, payment success, or a bad outcome might be payment failure. Okay? And this operator will produce all event patterns that are consistently leading to bad outcomes. Okay? And now you can use this operator in slightly different ways to get different kinds of analysis. So for example, if you restrict the set of events to user actions on the client-side device, this operator will tell you which user action sequences are leading to application errors. You can also limit the set of events to all backend events. and then this will tell you which backend event sequences are causing bad outcomes. So when you are developing an expert, you can use this as a building block, and all you need to know is the input-output signature of this building block without worrying about the underlying implementation of this operator, which can be complex and can involve certain complex algorithms, but all that is abstracted away from you as an expert developer. Here is another operator. This is a SQL operator that takes as input a metric name, such as login success rate, and it produces a time series for each user cohort. So a user cohort is defined by certain user attributes, like let's say CDN, ISP, device, operating system, and so on. And for each user cohort, you get a time series for login success rate. And again, you can use this data structure for different kinds of downstream analysis. Okay? And we have 30 operators like this in our library, which you can use to develop experts. And so they have like different functionalities. But at this point, you might ask about how did we arrive at this set of 30 operators. Okay? And the way we did it is by naturally letting the library of operators evolve over time. So we wrote our first expert, and we added the operators that we need to the library. Then we wrote the second expert, again adding the operators that we need to the library. And by the time we had developed a few experts, we also had a pretty expressive library. Okay? Okay, so let's say now we have the DAG. How do we efficiently execute the DAG? Because it involves different kinds of compute operations. Now, in the interest of time, so this is the third idea. I mean, we have a runtime system, which we call the lazy DAG runtime system. And in the interest of time, I'm not going to go into too many details about this, but you can check out the paper. But the core idea of the lazy DAG runtime system is that we employ a lazy execution technique, similar to other systems like Spark. And the benefit, one of the main benefits, is that you get to see the entire DAG ahead of time, so you can plan your compute operations better. You can schedule them better. Okay? So those were the three high-level pieces. So let's put all of these pieces together in an end-to-end architecture for a RCA system. So we have our library of experts that we developed using our operators, and these experts cater to different kinds of failures. And this library feeds into a policy layer, which is like the brains of the RCA system. And this policy layer has two key pieces of intelligence. Given a failure incident, what experts should you run? So this is kind of like expert routing. And then once you run those experts, how do you combine the output of those experts to get a unified list of root causes? Okay? And you can play around with these policies. Okay. So then the policy layer passes off these policies to the control plane, whose job is to translate these high-level policies into an executable MoCE DAG. And then this executable DAG is passed on to the execution plane, which schedules all the database and compute operations. So this is the end-to-end architecture of our RCA system. Okay? And we've currently implemented this in Python, and we currently have more than 15 experts for different kinds of incidents. We've implemented the stateful processing engine using a simplified, in-memory Python implementation, but we can improve that in the future. And I mean, it works fine for our use case. And then we have also built the lazy DAG runtime system as a layer on top of Ray, and it supports things like caching and parallelism. So you can refer to the paper for more details. Okay, so let's see how well MoCE does. So we evaluate MoCE on a diverse set of incidents that we created by injecting failures on the client side, in the network, in third-party services, and in the backend. And all of these failures are inspired from incidents that we saw in production. Okay? And MoCE achieves high coverage and high accuracy across these diverse set of incidents. So this is a graph that shows recall in top k on the y-axis. So that recall in top k means that if a scheme gets the right answer in its top k, we give it full points. And if you look at top 5, then MoCE achieves 95% accuracy, whereas all others are lagging behind 30%, including a LLM-based solution. And this experiment involves more than 10 different types of incidents. So you can see that MoCE is achieving high coverage over a diverse set of incidents. Okay. And we also ran MoCE as a pilot study for four real-world media services for about a week. And MoCE flagged different kinds of incidents. So I've just highlighted some of these. So in one case, there was a URL which was causing an issue. There was one case where there were two particular cities which were experiencing issues, probably hinting at some network problems. Then there was like a specific device that was resulting in problems. And overall, we showed this to a domain expert, and they were able to verify 9 out of 10 of these incidents. Okay. So overall, MoCE achieves high coverage, but what about scalability? So we ran MoCE against a baseline where you run the mixture without our framework. So each expert is run individually. Okay. And as you increase the number of experts on the x-axis, you can see that the runtime of this baseline increases linearly. Okay. So that's the green line. And that is expected, because as you increase the number of experts, the runtime will increase proportionally. But for MoCE, you can see that the runtime actually flattens as you increase the number of experts. And it saturates because even though you are running more experts, the size of the MoCE DAG does not increase by much. Okay? So you are saving a lot on duplicate computation. In fact, if you're running 15 experts, MoCE is saving about 6 times, is running 6 times faster than the baseline. Okay. So to conclude, we developed a mixture of context-aware experts framework for troubleshooting internet scale services, and this framework has 3 high-level ideas. We use a mixture of context-aware expert scheme. We have an abstraction which you can use to develop experts easily, and we have the lazy DAG runtime system that powers the framework. And even though we developed this framework for troubleshooting internet services, we believe that MoCE's abstraction it can enable comprehensive RCA systems in many other domains, like, let's say, network failures, industrial control systems, hardware failures, and so on. And with that, that's the end of my talk, and I'm happy to take questions.